and we are going to be right after that. We are going to be on page 28. So right after your homework assignment that we were on, we're now on proving segment relations. I'll give you guys a minute to find that. All right, you guys, so segments, if you guys remember, were parts of a line without basically cutting off the parts that go on forever. And so there's a couple of ones that are in postulates and theorems. So a long time ago, some mathematicians created things called axioms and postulates, and those things are really just accepted truths. And what that just means is like they're so basic in understanding that they're accepted to be true. One of which was the ruler postulate. Like we won't actually really be using that, but the understanding behind that is like, let's say you guys had a segment and then you used a ruler. I'm just going to say that's cut off right there. You used a ruler to make the determination. To make the determination that this is 1 inch. Okay, so long as the ruler is lined up to the one edge of the segment, you guys all learned how to use a ruler back in grade school, that the number that's associated with it, 1 inch and whatever the units might be, has a 1-to-1 correspondence with a real number. A real number is just a number that it is representative of, in this case, the measurement of the length of that segment. So we can use a ruler to determine the length of a segment, and that's all the ruler postulate really says. Okay, and postulate, again, is accepted truth. The segment addition postulate is something we learned in the beginning of chapter 1. Okay, and with that, oh yes, this is page 28 in your packet, thank you. It's right after the homework assignment we had last night. So the segment addition postulate just says, let's say, can you guys go ahead and draw? And it's important that you guys draw these things as you're going to, if it's not given to you. You're given a segment, and let's say that segment is A and C. And you have some point in between A and C. Okay, so they are collinear. And I purposely drew it so that it's not in the center. That B is between A and C. And you guys then are asked, well, what can you conclude about that given picture or the fact that B is in between A and C? The only possible conclusion you can make is that you have this piece plus this piece equals the whole piece. Okay, so you'll hear me informally say it as it's the piece plus a piece equals a whole. So that's this statement that you guys see right below, is that if you're given that B is A, B, and C are collinear, B is in between A and C, that's the conclusion that you guys can draw, okay? All right, so what we're gonna do is start off with a super easy proof that's guided for us. So if you scroll down to, or I'm scrolling down, if you guys look down at problem number 1, actually before I get to this one, I do wanna add one other definition here. So if you guys can write this on top, we've already defined this in the earlier part of the unit, like this packet. We have the definition of midpoint, but I just want to write it out here as well. And what this says is that if R is the midpoint, is a midpoint, midpoint has the word mid in it and point to say that it's the middle point of QS, then let's say what can we conclude? Okay, so let's say we drew a picture. You guys have Q and S. R is the midpoint, so we're going to draw it right in the middle. What can you guys conclude? And if you guys can have your chat out, and then you can either private chat or chat to everyone. What do you think you can conclude? If you know that R is the midpoint of QS, can you state something that you know must be true?
QS is the endpoint.
Yeah, the Q and S is the endpoints. Equal distance, perfect. So, and so some of you guys said it equal distance. Some of you stated QR is equal to RS. And QR is equal to RS means that the segment QR is equal in measure to RS. And so so those conclusions are going to be your steps. Like if you're given that something is the midpoint, your conclusion is that the segments are congruent to each other. The small segments are congruent to each other. Okay, so let's take a look at proof 1 now. Okay, so I still remember my geometry teacher being really, really anal about, write your given, write your proof. If you didn't have that, you didn't get any credit for it. And I see the reasoning why now. It's important for you guys to actually, look at the given, mark it off in your diagram. So BC, the measure of BC is equal to measure of DE. And the only thing you guys should mark off is what's given to you. So BC is equal to DE. I'm not going to mark out my proof one because the proof is what you still technically don't know that that's necessarily true. So it's like when you guys are solving an equation and then you just say like, okay, this is my equation, this is my answer. I'm just gonna accept that the answer is true and plug it back into the equation. That's checking your work, but that's not actually showing the work, right? So we're gonna read the proof and try to, use strategies like, okay, I could work backwards, but I'm not going to draw on the diagram to say that that's true. So proof part, I'm going to read it. Okay, so AB, this segment, plus DE is equal to AC. And so what I was given was BC and DE are congruent to each other. What I'm going to note in the proof is that, where they talked with the given about little pieces of a segment, in the proof part, somehow we have to incorporate this whole segment right here, which is comprised of AB and BC. So at some point, in a lot of the segment proofs, you guys are going to use segment addition postulate to tie together pieces of a segment with the whole thing itself. Okay, so BC is equal to DE. Statement 1, if we had to do a proof, statement 1's always something you should never leave a proof blank. You guys can always write the given as the accepted truth. And then from there, again, it's like, how do I link all of this together? If I know in my proof I have to get to AC, I'm going to write a statement that I know is true. If I know B is between A and C, according to the segment addition postulate, what would you guys know is true about AC if B is between AC? And Mia, look at AB and AC. They couldn't possibly be equal to each other, right? AB is equal to DE. No, nothing tells me that that's equal to each other. Oh, you wrote it wrong. Okay, I see someone responded correctly, so I just, AB is equal to BC. No, that wasn't stated to us, and it wasn't said that it was the midpoint either. All right, you guys, so if you know that B is in between AC, if you know that B is in between AC, you know that this piece of it, the pink plus the yellow, is equal to that green. Okay, so very good. Some of you guys have it. So in the segment addition postulate, you would know that AB, so you're trying to build up to the whole segment being AC. So AB plus BC equals AC. Okay, and so if I look at what I have right now in 2, and I look at what I have in 2, and I look at what I'm trying to prove, it looks like the AB and the AB are there. It looks like the AC and the AC are there. But somehow, I have to get from BC to DE. And so you're like, okay, well, what else can I do? In a proof for geometry-wise, you guys have to think of the steps collectively. Like, how am I going to use steps 2 and 1 together to make this conclusion about 3? Okay, so whereas in an algebra proof, like step 1 goes to step 2, and then you use step 2 for 3. In a geometry proof, you have to think of everything together. Like everything that's above might help you guys conclude about 3. So if I think about 2 separately, it's not going to help me with 3. I have to think of both of these together to help me think about this. And so Princeton noted that BC is BC here. BC is also equal to DE. So what we can do is substitute out this BC with DE. Plug that in, okay? What is another word for replace or plug in? What property allows you guys to do that? Very nice. Yeah, so let me see if anyone else responds. Okay, good, good, you guys. So substitution property, those are gonna be really, really common for us. Okay, so we're replacing something, it's called the substitution property of equality. Okay, so now let's look at number 2. In number 2, you guys are given, so this is a very basic statement. Q is between PR. Okay, you're given a number of things. Q is between PR. So what I would go to is make sense of that in the picture. Okay, yes, Q is between PR. The only thing at this point that I can make a conclusion about with this is Q is between PR. Is not that PQ is equal to QR, because it didn't say it's the midpoint. It didn't say bisect. It just said Q is between. And when it's such a basic statement like that, the only thing you could use is segment addition postulate, like PQ plus QR equals PR. So I keep that in mind. And then the next statement is R is between QS. So again, I can't really mark it, but I'm going to go look at my picture and see that R is between QS. And same thing in the back of my mind, the only thing I could conclude is that QR plus RS is QS. And then finally, the last thing that I can mark is that PR is equal to QS. So PR is this entire segment here. QS is this entire segment here. And so what I'm going to do is, because it's a larger segment, I'm just going to make a note that those are equal to each other. So I'm going to draw those funny looking braces, and I'm going to write equals, because I know that those two segments are equal to each other. And then finally, I'm not going to mark on my diagram, but I'm going to note what they want me to prove is that PQ is equal to RS. So one thing that you guys should be aware of is that what was given to you guys, this whole thing and this whole thing, were bigger segments comprised of smaller segments. And because you have a big segment that was given to you on that you know are equal to each other, but you're trying to get to smaller segments, then perhaps at some point you're going to have to break apart the small segments and make a relationship with the bigger segments, which always results in segment addition postulate. Okay, so those are just kind of the tips as we go along the way. Okay, so for me personally, I just list all of my given at once. You guys can see that this person who did this one listed only one of the given statements, which means that some of these other statements might be given. Okay, so they worked with just the first given statement, Q is between PR. And then from there, the only possible conclusion you can make from that is not anything that the pieces are equal to each other, but the piece plus a piece as a whole. What is that? What is the reasoning for 2? Why do we know PQ plus QR is PR, is equal to PR? Okay, perfect. So go ahead and write, yeah, so you guys, you don't, if they don't tell you guys it's equal, you don't know it's equal. All you do know is that the piece plus the piece is the whole piece. And that's segment addition postulate, good. Okay, now they are stating R is between QS. Where did they get that information? How do I know R is between QS? What's the reason? Perfect, given. And once again, if you state all the givens at first, you don't have to restate it again, but this person chose to separate it and then just apply what they know for each one. So this time, they're stating that R is between Q and S. So what do you guys think the step 4 is going to be for the statements?
QR plus RS equal QS.
Yes, okay, and some of your letters might be swapped, which is perfectly fine. So as long as you guys have QR plus RS or something to that effect equals QS, a piece plus a piece equals a whole. Okay, so now we've kind of tied together the pieces, and one other statement that we know is PR equals QS. And let's say you guys forgot that that was given. You would know that it's given because you marked it off here. Okay, so you know it's equal to each other because it was given to us. And now I want you guys to think again, an algebra proof is just a step before that, right? Just a step before that. A geometry proof is all of this information together leads me to conclude 6. Okay, any ideas? How did they get from all of the steps, namely step 2, step 4, and step 5, to make this conclusion here? I'm going to quietly highlight. It wasn't something that was given to us. I'm going to quietly highlight this and see if you guys can make connections. So I highlighted something in yellow. Okay, so if you guys look at the chat, Jenny guessed substitution. Some people guessed transitive. Both of those are correct. Okay, so if you know that something is equal, if you know that PR is equal to QS, couldn't we say that we can drop PR and QS and set these guys equal to each other? And that's statement 6. Okay, or another way of thinking about it is you have PR here and PR here, and PR is equal to QS, so I'm going to replace this PR with this statement right here, which is QS, and put it over here. And that's going to get me statement 6. So a lot of times, substitution property and transitive property are interchangeable. Okay, so hopefully that step makes sense to you. That's a common thing to do. I'm going to have you guys cross off step 7 because when we were doing our algebra proofs too, we didn't show this step and I think it's just an unnecessary step. So you're going to cross out step 7 and call this step 7 and then erase also what reason 7 will be. Okay, so now when I look at what I'm trying to prove PQ is equal to RS. Okay, so I noticed that on both sides of step 6, I have QR and QR in it. In your algebra proofs, how did you guys get rid of that? How'd you guys get rid of the QR? How'd you get rid of a number that was on both sides like that? What property? Yes, good. If we have some number on both sides that is added, we can subtract both sides, QR from both sides, and we get PQ is equal to RS, and that is by subtraction property of equality. Okay, so from there, we're going to scroll down to, or flip the page to page 29. And then I'm just going to mention a few things is that you guys don't have to find this page. I'm just going to show you something real quick. Your previous, let's see, okay, your previous homework assignment on algebraic proofs, don't find the page, just look up. These are algebraic properties of equalities. If you guys notice, all of your signs here are what we call equal signs, right? Equal signs, equal signs, equal signs here, they're all equal. So these are properties of equality. So I would say that these last 3 right here, they also have similar properties, but instead of equalities, they're of congruence. Okay, and so the difference between something being congruent versus something being equal is that congruence is talking about shapes. So let's say we're measuring segments. We're saying they're the same size and shape. When we're saying that they're equal to each other, we're saying that the actual measurement, like the numeric measurement, like 1 inch, for example, segment AB is equal to 1 inch, that's a measurement, so that's equality. Again, congruence is shapes and equality is actual measurements. Okay, so let me go back to the page that we were on. And at the top, you guys can see reflexive, symmetric, and transitive, these are now properties of congruence. So when you say it, you can say reflexive property of congruence. Now, I'm not going to be very picky about equality versus congruence for these properties. So just recognizing that sometimes you might see in a step that they're congruence instead of equality is good enough for me. So let's look at steps or these problems right here, problems 1, 2, and 3. What do you guys think number 1 is? If DE is congruent to GH, then GH is congruent to DE. What property is that? Okay, good, Mia. Okay, so that is symmetric property. And if I wanted to be specific, I would say symmetric property of congruence instead of equality. All right, step 2. Okay, and I'm going to make note of this as there is, again, some people view it all as one type of property, and then others can see it as 2 separate properties. But 2, what is one property that says if AB is congruent to RS, RS is congruent to WY, then we know AB is congruent to WY. Okay, very good, Mia. So you see how RS is repeated. It's kind of like skipping over that middle person. And this is transitive property of congruence. And every transitive property can be easily explained with substitution as well. So if I know that this is equal to RS, then I can substitute WY in its place. That's fine if you guys use substitution property as well. Okay, last one. If RS is congruent to RS, segment RS is congruent to segment RS. Very nice. Okay, reflexive is going to be used so often when we get to our proofs of triangles. Okay, so reflexive property of congruence. And then I'm going to have you guys, I'm going to change coloring and just have you guys write out one thing. And this is definition of congruent segments. We've defined this before in the previous notes in the first few pages of your notes in this packet, but I'm going to go back to it now and just have it here so that we know we can use it in our proofs. But if two segments are congruent, the only possible thing you guys can conclude from that hypothesis, if 2 segments are congruent, then their measures are equal. Okay, and the reason I'm putting this here is it's used quite frequently in the segment proofs. And something to note is that when you have a definition, its converse is also true as well. So if you have if you had it going the other way, if two segments have equal measures, then the segments are congruent. That's also true, and that's all definitions. Okay, so that's something to keep in mind. Mia says she doesn't understand reflexive. Reflexive is just like 2 equals 2. It's an accepted truth. It's something is equal to itself. And later on, when we move on to shapes, this side is congruent to itself. Okay, and it just means that something, by definition of what reflexive property is, it must be congruent to itself. It's like the shared wall on one side of the room and the other side of the room must have the same length of measurements. And that's reflexive property. A number is equal to itself. A shared side is equal to itself. Yes, it's like the simplest property pretty much, yeah. Okay, so down on below, you don't have to flip the page, but I want you guys to notice something. Here in your given and proof, you have congruent statements. Okay, congruence. And you have that little bar above that. So when we use the congruent statement, we do have to put the bars above it. If I scroll up, the 2 proofs that I've already done, okay, they didn't mention congruence. They mentioned equality. And when I look at my segment addition postulate, it also uses equality. So if I'm going to use my segment addition postulate, I'm going to have to somehow convert congruence to equality in order to use this. It's a simple conversion, Okay, and it has to do with this right here. Okay, so now first up in this proof, our last proof here, we have PR is congruent to QS. Because that's given to us, I'm going to mark it off. And PR is a larger segment than just one of the small tiny pieces there. So I'm just going to mark off with the braces PR is congruent to QS and put an equal sign there to know that that is something I know. That is given to me. Okay, what I'm trying to prove is that PQ is congruent to RS. And PQ, this sounds really familiar, right? PQ is congruent to RS. And these are pieces of the whole segment. Okay, so the problem is that, okay, well, I know that eventually I have to build up to connect the pieces with the whole piece. So at some point I'm going to need segment addition postulate. The problem is that segment addition postulate is equality and this is congruence. So I'm going to write from step A to step B, I'm going to drop the congruence symbol and write equals and drop the segment symbol to not include that in here. So PR is equal to QS. From something that we just discussed, you guys, why do I know that if PR is congruent to QS, that I then can conclude that PR, the measure of PR is equal to the measure of QS? Not given. The only given part was PR is congruent to QS. What else could it be? Look above, like something we just wrote down. Yes, which definition? Yes, good. So definition of congruent segments allows me to say if two segments are congruent, then their measures are equal. Okay, so now that I've converted that to equality, I look back at my picture and I need to somehow build the segment, the pieces and the holes. So I see that the next statement is PQ plus QR is equal to PR. So what allows me to say that? PQ plus QR equals the whole thing. Segment, good. Segment specifically, good. Segment addition postulate. And so that only gives me one of the pieces that I need eventually. The other part is this side, right? So what else do I know is true? Very good. So QR plus RS is equal to QS. Okay, and then that's by segment addition postulate. I now, again, different from algebra, I'm going to consider all the steps that I have above and see how I could possibly conclude PQ plus QR equals RS. Okay, so I know PR is equal to QS. How do I make that conclusion? You guys have PR here. You guys have QS here. You have PR is equal to QS. Yes, it's substitution property. Symmetric would just be like x equals 6, then 6 equals x. It just reverses the order. It's substitution because you guys are taking, you're removing, let's say you know this is congruent to this. You're removing those and then replacing this in that spot. Okay, so substitution property. And then of equality. For F, we notice that QR is on both sides. So then what do? We subtract it to get PQ is equal to RS. And then finally, those two are equal, but our proof part is congruent. So I'm going to write down what we have. PQ is congruent to RS. How do I know that? That's also by definition of congruent segments. Okay, so what we're gonna do next, we're in the same packet. So if you guys can stay in the same packet, I'm gonna scroll down to page 48 and we're gonna practice with some of the common segment statements that you guys will see tonight. sorry, that's not page 48. I accidentally moved a page, so let me switch it back. Okay, so scroll down to page, there's a lag here. Okay, page 48, making conclusions. I want you guys to see these problems as like the beginning of the proof. Let's say that you had statements on this side and reasons on this side. And let's say in problem number 1, you guys were given TO is congruent to AN, and they just wrote that that's given to us. We know that that's given. Okay, and then when they ask what's the conclusion, that's like, what's statement 2? And the justification is, what is the reason that I know statement 2 is true? Okay, so TO is congruent to AN. The only possible thing you can conclude from that is that its measures are equal. Okay, so think of the proofs. If I'm given that they're congruent, the only possible thing I can conclude is that they have equal measures. And the justification for that is what we just used, definition of congruent segments. Okay, so try to only focus on what's given to you and then what possible conclusion can you draw. Okay, so the key, look for keywords. This word has midpoint in it. So E is the midpoint of BD. So you guys have E here. What's your conclusion? Any ideas? What could you guys conclude if E is the midpoint? And many people, when they're given that it's the midpoint, yeah, good. They automatically just start marking like that. And that is your conclusion. You know that BE is equal to ED. And use that word to help give you guys a hint. What's the justification for that? What's the reason for that? The only thing we know of is, good, definition of midpoints. Okay, here's a new one. And it's very similar to the other one. This is going to be a keyword, bisects, right? We have point A bisects CT. So CT and then A in between. If you guys had to mark something on the diagram for that statement, what would you guys mark? If A bisects CT, what would you guys know is true? Okay, good. If it bisects, it cuts it in half. So you know CA must be equal to AT. Well, that looks really similar to the definition of the midpoint. The reason why I know my justification isn't saying definition of midpoint is because of the word bisects. So definition of segment bisector. Okay, number 4, you guys have, okay, I noticed that, draw pictures for these, you guys. I noticed that it says CO is, so it looks like CO is being repeated. So CO is equal to OL. CO is equal to OL. Yes, and Mia, I would say your justification is different only in that what was given to you was midpoint and what was given to you here is bisects. And so that's how you tell the difference. Oh, did I write something wrong? Yeah, thank you. It's AT here, guys. Thank you. So for 4, you guys are given CO is equal to OL. What's your conclusion? Okay, so I want to point out something that, yes, I want to point out, can you guys look at the chat? Someone wrote that CO plus OL equals CL, which is true, but the fact that they're talking about equality, you want to conclude something about that relationship that was given to you. CO is equal to OL. Even though I know CO plus OL equals CL, that's like something that I can conclude if I didn't know anything about the equality. But if I do know that it is equal to each other, then Mia is correct. You guys have that O must be the midpoint of CL. Okay, so this is kind of like the converse of the definition, but O is midpoint of CL. Or you guys can say O is the bisector, in which case you guys can use what you just concluded. So this is definition of midpoint would be okay to say. You guys could say O is the bisector of CL, and you guys can say definition of bisector, that also works. Okay, so the difference between why I concluded that versus number 9. Now, if you guys look at number 9, it's just a picture, you guys, right? It's just a picture. So in that picture, can you say stuff like EF is congruent to FG? What do you guys think? Yes or no? Do you know EF is congruent to FG? Good that you guys said no. Okay, because that's probably the number one mistake I see is over assuming things. It looks congruent, but it wasn't given to us as congruent. Okay, so then what's our possible conclusion? The most basic conclusion, if you guys know F is between EG, yes, but what else can you conclude if besides F is between, if F is, we can't conclude it's the midpoint because we don't know. It just looks like it, but they didn't say this is equal to this, so it can't be midpoint. Very good, you guys. Yes, your conclusion is EF plus FG is equal to EG. And what's the reason? A piece plus a piece. Segment addition postulate. Okay, this, you guys, these are basically the possible answers that you guys get when you're doing, besides the properties. So I highly emphasize you guys work on like just trying to remember this stuff that we've covered today, because the angle ones get to be a little, I know the angle ones are more intimidating for students. So what I'm gonna do, since we're already on this packet, you guys, I'm gonna, because I think flipping back and forth between what you guys had before,